Should I start?
Wait a minute or two.
I start writing some
Yes.
I don't resist.
Get a few blackboards ahead of them.
Yeah,
Okay. I think you can start.
I think I can start. So, so last time I was discussing. Last lectures we were discussing this dimer model that in fermionic language takes this form. So the interacting partition function compared to the non-interacting one is given by a sort of fermionic phi-4 model, in which you have an interaction that is quartic of this form, minus 2 alpha sum over the size of a square lattice of this interaction here. Alpha is just essentially lambda. At this level you can even forget about the lambda. P dip psi is Grassmann-Gaussian integration with propagator gxy given by this formula. This is well, the infinite volume limit at fixed x and y's. If you have finite L, you have just Riemann sum with spacing of order 1 over L. So the finite L gives you an infinite regularization of the of this propagator. The reason why I say that is that this mu of k has singularities. So mu of k is equal to 1 plus I e to the I k1 minus e to the I k1 plus k2 minus I e to the I k2. It turns to be 0 if and only if k is equal to 0, 0 or pi pi. These two singularity points are referred to as the Fermi points, which I labeled P plus P minus. And the singularity around this pole, around this these zeros is simple pole. So if you shift by p plus minus at linear order, mu behaves like minus I minus omega k1 plus minus I plus omega k2. So it's this at linear order plus order k squared. Here omega is plus minus. So already on Friday, Fabio discussed, and last time I reminded that if you try to perform naive perturbation theory by expanding the V of psi and order by order computing the average with respect to P dip psi of the product of the V's using the fermionic big rule, you get a certain class of diagrams that appear to be divergent. If you look into them, you recognize some cancellations. You have the idea of making some resummations to solve some of these problems, but in order to systematically do that, you're led to analyze these objects in a multi-scale fashion. So what you first you pass to sort of in a sense coordinates adapted to the location of the two singularities by rewriting gxy as a combination of of two propagators that in a sense are centered around the singularities. Which I call, for reasons that will become clear, maybe already became clear last time, G omega smaller equal than 0. So this G omega smaller equal than 0, xy is nothing but the shifted Fourier integral in the vicinity of the singularity with an extra characteristic function that restricts momenta to be approximately. So this is roughly speaking a characteristic function that k is smaller than pi. Not exactly that, is a smoother version of that. Okay, so correspondingly we rewrite the fields, the fermionic variables like this. Use the addition principle to rewrite the object of interest as a measure that is a product over the Gaussian integration of psi plus, Gaussian and the psi minus. Here I mean the plus minus of these omega indices of E. So this is just the same as before, in which V of 0 is rewritten in terms of these new independent fields labeled by this index omega. And now I start to split up this into scales. From now on, the omega index is understood without writing it every time. Where these are the two, so this decomposition is corresponds to the maybe we can do this. This decomposition corresponds to the decomposition of the Grassmann variables in two independent fields. With propagators correspondingly G0 omega xy, G smaller equal than minus 1 xy, which are essentially the same as G smaller equal than 0, with the difference that the cutoff function is replaced by another cutoff function. So here is replaced just by this thing, which I call f0. And here it's the same times pi 2k. Okay, so this guy is the single scale on scale 0 propagator, which decays, morally speaking, exponentially without oscillating prefactors. Derivatives scale also exponentially. And this guy here, so this okay, so here the approximately equal is well meant maybe as a bound. Yeah, to any dimensional purpose you can replace this object by this. And this, if you recall the almost linear behavior of mu of k plus p omega, you see that you can rescale. This is approximately the same as 2 to the minus 1 g P0 computed at coordinates 2 to the minus 1 x, 2 to the minus 1 y. Okay. Questions so far? There was.
So fermion fields look like this scale with dimension 1/2?
Yes. Okay, so last time we also discussed the result of the integration of P0. So if you integrate out P0, you can write you can write what you get in terms of an effective potential on the next scale, which I call V minus 1. Up to a term which is a contribution to the pressure or free energy. So this thing here I write as E L squared e to the minus 1 plus V minus 1 of psi smaller equal to the minus 1. And this combination can be written as follows. Okay, this is essentially by definition of this truncated expectation. What we discussed last time is that this object actually this series is convergent in the following sense. So this is this expression is formally well, a constant. This plus sum over L even and non-zero of something of the following form. Where this this graphically becomes the following. So this generic term graphically you can think of as a new effective vertex. So the kernel of a new effective vertex with L external x. In the example, L equals 6. This object is an analytic function of alpha, and this is essentially local, is exponentially decaying on scale 0. So and this can be quantified in terms of a norm. Well, last time we discussed only the unweighted L1 norm. But, okay, before I discuss norms, let me write a formula for this. So we actually, so the procedure above allows us to get a formula for this object in the following way. So this is equal to, okay, so here I will try to use a notation that will be useful also in the following. So this becomes 1 over m factorial. Okay, so let me write something relatively complicated, and then let me comment about the meaning of that. just a second. So this is a formula that I didn't write exactly in this formula last time, so let me explain what I mean by this. So in this formula, I'm implicitly rewriting the original interaction, so V0. Okay, here, no, sorry, here there are, no, there are some sums missing. Just sum over the coordinates. Okay, let me explain. Maybe like this. Upstairs. So I'm assuming here that each vertex, so remember V0 of psi is was what? Was minus 2 alpha sum over x psi plus x minus x psi x plus e2 psi minus x minus e1, in which each field should be thought of as the sum over omega e to the I plus minus. Okay, so this was the definition of V0. Here, each of these guys should be replaced by a sum of two guys. I will symbolically write this in the following form. So I introduce a set of labels 1, 2, 3, 4, indicating, say, the first guy, the second guy, the third guy, the fourth guy, and I will symbolically write this in the following form: x of t. So by this I mean the vector x1, x2, x3, x4, omega p, v omega p x p of psi p, where psi p is just the product of psi plus x1 omega 1, psi minus x2 omega 2, etc. So this is just an ordered product of psi so it's ordered in the same order as the t, and this is whatever the kernel associated with this. So there are some oscillating factors, some delta functions that tell you that some x's are equal to others, or the difference is equal.
You have a minus 2 alpha, no?
I insert it into the curve. So okay, so when I compute what?
Is there a product there or no product?
What, where?
Before the V's? Or what's the J?
Yes. Okay. There is no. Thank you. Okay. So what do I do? So when I compute this the truncated expectation up there, I just replace this expression up there. So I have so the action of the truncated expectation is multilinear. So all the sums and the v's goes out, and this is what you get here. So there will be a p1 pn to indicate the various indices of the n groups of fields. So I have these sums, I have these guys, and then if I want to extract the term corresponding to L external x, for each group I should extract a subset of fields that will be the external line. So for each group I choose which ones are the psi zeros and which ones are the psi. So the psi are the external guys, psi zero are the contracted guys. So I call these are the external lines. So they are a strict subset of P1. You need at least one guy to connect, so they cannot be all external. And there is a constraint that the number of external lines should be L. So the union of the QIs should have L elements. This is indicated with this guy. Similarly, all the x's, etc., should be summed with the constraint that you fix the labels of the external guys to x and omega, and again you indicate the constraint like that. And then you have the truncated expectation of what you're left with, up to a sign from the permutation that you need to take out the fields you have not integrated. Does this formula make sense?
Do you have to sum somewhere over the x's for the q's? So
Do I? Yeah. Sorry, it was up there and I forgot. Thank you.
But also in the w?
No, W is a fixed x.
Oh, it's
Okay, okay. This is the definition. Okay, so last time we also discussed that this E0 admits a good combinatorial representation in terms of the Bridges, Battle, Feather, Bush, Kennedy, Besselam, Rivasso determinant formula. One version of which is the following. I hope I can write it for the sets labeled like this. Okay, determinant formula for the truncated expectation. This is a sum over spanning trees connecting these blobs. So you should imagine that each of these guys is a blob with Q1 minus Q1 external x. Some of which could even be odd. Okay, so you're taking an average of these guys, and you want to contract them in all possible connected ways using the Vic rule. There is a sort of resum formula for the Feynman diagram expansion of this. The formula being something of this sort. So you connect these guys in a minimal way with a so-called spanning tree. So you define a set of lines that connect in a minimal way these blocks. You have some sign coming out of the permutation that well, comes out of the construction, but will not be very important for us. You have the product of the propagators associated to these lines, G0 L. Let me write like this without specifying omega L XL minus. Okay. This comes with all its indices. And then you have to contract in all possible ways all the other Grassmann fields that you're left over after you contracted those along the spanning tree. This is a determinant. To be more precise, you get a formula which is an interpolation of determinant. This I prime go from 1 to the number of propagators you're left with. So these T's are interpolation parameters. They are labeled by pairs of J's, where J is a label of this group. J goes from 1 to n. Each of these guys is between 0 and 1, so that this measure, this is a probability measure supported on T's that are between 0 and 1. Particular is a probability measure. And the measure itself may depend on the choice of the spanning tree, so I write T. I think I forgot this last time. And this G0 T is just is very simple. It's just Tj J prime G0. There are omegas that I left. I lost along the way. This is so if you have a propagator associated to a pair of x's, xi prime. These j and j prime are the labels of the groups pj and pj prime, which this variable belongs to. The important thing is that this is between 0 and 1, so the L infinity norm of this guy is the same as the L infinity norm of this guy. And the good thing now is that using such a formula you can get easily a bound on the, say, the L1 norm of this V minus 1.
Excuse me?
Yes?
So here, P1 minus Q1 is the set of external legs, or is it Q1? Because, before you choose...
Yeah. I'm calling external legs to different things. It's 5 in the example. So, maybe this is are the contracted legs exiting from this blob P1 minus Q1, graphically exiting from the first vertex. Yeah, because you see there were the really external legs, those that I don't integrate at this level, and those that I'm integrating. So somehow in this picture I took out the guys that will be integrated next. Then I'm drawing those that I'm contracting on this scale and then contracting. So in this picture here I'm writing only those that I'm contracting now. Okay.
So I agreed tomorrow to explain this formula to anyone who's interested. Henri, is it tomorrow that I agree? Yes. Yes, okay.
Okay.
I think it has to be the afternoon. Yeah. Lunch.
Okay, so you can, using this formula, you can easily...
Sorry, the small n is a large n in the formula for T-bar, or not?
No, this is, I don't know, another... so this is the number of propagators outside the spanning tree. If you like,
no, it's clear.
okay.
I got it.
But
Right.
you can say what it is. It's 4n minus L divided by 2 minus n minus 1. So for n is the total number of original lines. You have to take out the external ones, divide by 2 because each propagator comes with contraction of 2 of such legs, and you have to take out the guys that you already got here. So this is sum over x1 xl of so this is something I explained last time, but it's pretty easy. So this, if you want to compute this norm, what do you do? Okay, so here you have a translational invariant object. So you can use translation invariant to set one of these guys to 0 and compensate the L squared. Then the sum over all the other guys can be thought of as sums over the differences. Essentially, the differences appearing as arguments of the propagators along the spanning tree. So I will get, in terms of this formula plugged here, you get the following. So you get n larger or equal than 1 over n factorial. Then you have some constant to the n, alpha to the n. Alpha was the intensity of these kernels here. C to the n includes all the dirty stuff, which is, for instance, summing over the choice of these sets. I mean, you don't lose more than a constant to the number of vertices, 4, 16, whatever. If you think about it, you should get it. And then you get sum over spanning trees. This is up to a constant to the n, an n factorial that compensates this n factorial. Then you get the L1 norm of the propagators along the spanning tree. And then you get a uniform bound on the determinant, which is essentially the L infinity norm to the right power. And that's it. Because once you bounded this uniformly in T, this gives you 1. Okay, here I'm cheating a little bit. Maybe David can repair the cheating in the sense that to really do that, you have to really bound the determinant in terms of a constant to the n. You have to realize that your G is written as a scalar product. It has a gram form. It's written as a scalar product between two vectors, and the truth is that here, instead of having the L infinity norm of this, you have the product of the L infinity, well, the product of the norms of the two gram vectors. This is sort of side technical remark. I mean, for all the important thing is that this constant scales the same way, so it's the same up to a constant than the norm. Maybe, I don't know. I mean, so that I'm hiding a little technical trick, but which is important, of course. So the representation here must be such that even the interpolation parameters have the right gram structure. This is one non-trivial part of the proof, but maybe it will come out of the discussion. Okay, so out of this you get a bound that shows that after the first integration, your effective potential is analytic function of alpha, and is exponentially decaying. Yes, here this is just the regular L1 norm, but without any additional effort, you can also weight this by an exponentially growing factor, provided the growing factor is as a constant that is beaten by the one in the propagators. So if you have exponentially decaying propagators, as we have, and you add an exponential weight, you can decompose the weight on the propagators, and okay, so you can get exactly the same qualitative estimate with an exponential weight, and here you will have the weighted L1 norm for this propagator rather than the So the same proof also shows that these guys are exponentially localized, where exponentially means at the same rate as the propagator. Okay, next I proceed. I do the same from -1 to -2. Where, okay, I hope it's clear now. And similar for g smaller or equal than -2, it will be given by the same expression with chi 2 to the power 2k. Yes, let me add a comment before I proceed. So in principle, so now that we did the first step, in principle, if we really proceed as I suggested last time, we should look for some partial cancellations, start to make some resummations of the potentially dangerous terms, and then go on. So we should first manipulate a little bit the v-1 before proceeding to the next integration. This is what we ideally and actually a posteriori will need to do. But to define effectively the effective in the sense in a good way the resummation procedure, we need to know what are the potentially dangerous terms. So in my discussion last time, I suggested, I recognized some potentially divergent terms, but I'm not sure yet that these are all possible divergent terms. So I want to preliminarily classify all possible divergent terms and then define the right resummation scheme. So to do that, I will temporarily proceed without any resummation. So I proceed blindly in a multi-scale fashion, but will perform bounds that will allow me to identify what are the potentially dangerous terms. Next, I will go back to the procedure. Once I identify them, I will go back to the definition of the procedure. I will adjust it so to cure these terms. So in principle, I could give you directly the receipt, but it looks a bit mysterious if I give it directly. Okay, so I make this this thing, and then I compute the.
Formally, aren't you just going to extract some quadratic and quartic term, or not?
This is what I will do. But I would like to. I guess you know. Maybe not all the. On the basis of what I said, I should do something at least to the quadratic and quartic terms because
They get renormalized.
Yeah. But in principle, there could be other diagrams that I didn't identify yet. So I would like to check that in fact nothing is left, nothing else creates troubles but those two.
So once you absorb the quadratic terms, you're changing all the future propagators that you haven't integrated yet. Is that right?
Yes, you're going.
So right now you have still the propagators that you haven't integrated, right?
Yes.
But once
Now temporarily I will not do anything, but a posteriori I will have to do. So a posteriori, I will have to localize.
Right, my question was a technical one, maybe I'll get back later.
Okay. So for the moment, I'm doing the trivial one without any particular summation, but I will get back either at the end of this lesson or more probably on Friday to the definition of the correct one, in which I have also to reabsorb part of the quadratic terms into the propagator on next scale. So so I iterate, and what I get is exactly the same kind of expression. So this guy here now will be given by the same kind of expression, and okay. So here I get all the same kind of expressions when I go on the next scale, with the difference that these kernels here will now be the kernels on the previous scale instead of being the bare ones. Is this clear? So I do let me not erase this. Maybe also that. Okay, maybe I will revise. So you see, v minus, remember, when I integrate W2, so let me remind once more. So when I so v minus 2 is the result of the integration of this p minus 1. This v minus 1 is what? So remember, this is a formal series. It's a series of objects like this. 2-leg diagrams, 4-leg diagrams, 6-leg diagrams, etc. Each of which has a kernel w minus 1 with the right number of legs. So to construct this guy, I have to take the truncated expectation of all these guys. So I have to sum over all the possible. Okay, now there is a sum also on the choices of P1. So now there is also a sum. So here now I have to sum over the P's. Yes. I have to sum over the Q's with some constraints that the number of external legs should be again 1L. for the rest, I have the same kind of expression, but now I have the kernels on the next scale instead of the original ones. Does this make sense? Okay. Now, if you zoom in, each of these guys, you remember, was again a sum over whatever. Actually, let me. Okay. Sum over, I don't know, S1, 1 over S factorial E0 of blah blah blah. And similarly for the others. Okay, so I can each of these guys, if I recall, was given by a similar expression on the previous scale. Okay, and this structure of sums into sums will be represented graphically this way. So these are the trees that Fabio already anticipated last Friday. So I have a sum over n larger or equal than 1 of an expression that I graphically represent this way. This is a graphical representation at a different level than the Feynman diagram representation. It's more a representation of this iterative structure here. So here I have n guys exiting. So I have this, okay, I have this node, which I will call the vertex, if you like, V0. And I have, in this example, n nodes following it. So this n lines exiting from the first node indicate these guys. There is a 1 over n factorial where n again is the number of lines exiting from this, and this vertex that represent the action of e to the e minus 1, truncated expectation with propagator minus 1. Now, these subtrees originating from this indicate the specific class of contributions of v w minus 1 that came from the previous stage of integration. So these represent truncated expectation on scale 0. And now these are S1 vertices, and now these final points, endpoints of the tree represent Bayer interactions. So each of these final points now represent a Bayer interaction. So I will sum over n and sum over S1 Sn. And the value of this guy as the factorials, and okay, as this truncated expectation, each of which can be represented with the dB, fk, etc. formula. So at each level, you have a spanning tree with its propagators, and you have a determinant with the propagators outside the spanning tree on that scale. So you get, after 2 steps, you get this 2 layers formula for W minus 2. So if you manage to digest this, it's done. All the rest is just a repetition of this.
So what that is small s? Can you get down the black?
Yeah, sorry.
You have this small s, so it's the number
Yeah,
of
maybe it's not.
Number of legs coming out of D1.
So it's one. Yeah, okay.
So I have this, so let me write it like this. So I have, let me indicate with n, yeah, maybe this notation is not consistent with what I will write next, sorry. Okay, so I will slightly change the meaning of n here. So now n so here n represents the number of bifurcations at the first, not bifurcation, I mean the number of branches exiting at the first level. In this other formula, n indicates the number of final, number of endpoints. So in this is what in this, yeah. So maybe to make connection, let me do like this. Okay, so there is an S, an S1, S, and n is the number. Also, this is not very nice. I understand. Okay. So here I have the sum over these trees tau with n endpoints. I have SV, so I call these V's are called like this because they recall the fact that these are like effective vertices. So there is this node V0, out of which SV0 lines are exiting, and it's followed by SV0 further vertices, which I call V1, V2, etc. And each of them is followed by SV1 endpoints and so on. So I got an estimate that now is very, very similar to what I had before. This symbol is not very elegant. Okay, I think it's harder to write than, so if you understand it, it's easier than writing all the details. So for each bifurcation you have one of, for each node you have one of these factorials. It's just the number of lines exiting. Then you have some constants that are of the whatever to the power this number of branching. Then I have for each vertex I have a spanning tree. Yeah. Okay. Sorry. So I have for the node V0 I have this spanning tree, which comes with the G minus 1 to the power SP0 minus 1, G minus 1 omega infinity to the number of to the dimension of the determinant on that scale. So the dimension of the determinant of that scale is EV1 is the total number of lines exiting from these vertices minus the number of external legs I still have to integrate, divided by 2, minus the guys that are already on the spanning tree. Okay, and then I have to count the number of spanning trees which I have on that scale, and this simplifies up to a constant c to the SV0 with the SV0 there. And then I have the same kind of structure for all the other so I have G0 SPJ minus 1 J0 omega to the 4 and J minus J. 4 SPJ times a number of spanning trees, so which is does this make sense? I mean, this.
So your S is the number of lines coming out of each vertex, V, is that right?
What?
The SV, like SV0 is the number of lines coming out of vertex.
V0, yes, SVJ is the number of lines coming
And what
out.
is the last one? SVS sub T tau 0 or something you've written there. I didn't quite know what that was. That's just the very last generation.
Yeah, it's SV, yeah, in fact, that is why I commented that this was an unfortunate notation. So you have SV0 lines coming from this. So if I number these guys, it becomes V1, V2, up to V of SV0.
Oh, I see. Okay.
Yeah, so it's probably not very, so this is VSV0. Yeah. Okay, I don't know, yes. I think there is room to improve the okay, besides this, is this here? I don't know, maybe you got lost, but so it's nothing. So I'm using this, so I repeat the thing twice. At each level, I have a truncated expectation, which I represent with the determinant formula. So at each level, I have the sum over spanning trees, and I can use exactly the same kind of estimate at each level. I just have to sum over, yes, so these trees, they come maybe, or I can even write it express. So this sum includes a sum over these choices PV1, PVSV0. So the endpoints have necessarily an ordered string of 4 labels. So there is nothing to sum. So I know what are the kernels of the bare points. But here I have to choose how many guys I'm left with, and here, well, I have to say somewhere also that that the number of things I'm left with on the last scales is equal to L. Okay, so okay. And now, as you may imagine, this structure can be iterated very, very easy. I mean, once you accept this, you will accept the several layers formula. So if you don't understand this, ask me. If you understand this, you should understand also the next formula. So I continue at each scale. I have to integrate the field on the next scale. I repeat. I will have a formula which I will have W minus 2. I zoom in, minus 2 is given by this expression.
Why you have to zoom in? Why you cannot just track?
Okay, yeah, yes, this is an interesting point. So for instance, depending on the problem, you can decide to just to write in this way and get an inductive proof for the norms of this effective potential. Okay, this requires that certain that your theory has certain special features. So, for instance, it works in theories in which you have a negative beta function, like 544 that was discussed if you in this theory, as you will see, the beta function for the effective interaction has very subtle cancellation. It's essentially zero at all orders. So if you truncate at any finite order, you won't be able to see the cancellation, and you actually have to work hard. This is what I will try to sketch next time. You have to work hard to conclude that in fact you have cancellations at all orders. So if you have in mind the mechanism that, for instance, Gordon was describing at the beginning of September, that mechanism typically you can play an inductive argument, and in parallel you have to start the beta function truncated at some order, enough to be able to control the flow of the effective coupling. Here, no truncation would be enough, because you have to prove that this is 0, 0, 0. So somehow, in a sense, you are forced, or at least nobody knows how to do this without. You have to re-expand at all orders and check some cancellations, and it's sort of inevitable to re-expand everything up to the last order. I mean, this is not a proof that there is no inductive scheme working in this situation, but nobody succeeded in performing it.
But Alessandro, the beta function in the end cancels to 0, right?
Yes, a dominant order is 0.
There must be a principle behind it.
Yeah, in fact, there are word identity. There is one has to show that the beta function of dominant order is the same as the one of the Tiering model, where you have chiral gauge invariance that gives you cancellations that are not exact in this lattice theory, but are valid for the dominant part of the beta function. More questions?
So for the cancellation, you're not going to be using bounds, you're going to have to actually...
Yes.
So the bounds, I guess, give you the right to talk about the object, and then you can see the cancellation after that.
Again, it's not impossible that there is an argument that avoids the complete expansion, but
just to make a remark before you go on. I mean, the point is that, I mean, for bounds, you could do, I mean, if the naive procedure will work.
Yes, you're right.
But then you want this cancellation, and then you.
No, you're right. I mean, if you give a black box name to the dangerous part, the local part of the quartic interaction, you could get inductive bounds involving this object, but the bounds you will be able to iterate the bounds only if the flow of this quartic coupling will remain bound. Now, if you try, usually the things go together. So how do you show that these effective couplings have a bounded flow? Typically, you write the beta function, so that the function controlling the flow with the same kind of expansion you used before. And you argue that this is negative, for instance. If you want to show that it's 0, you have to really look into the full expansion of that. So I have the impression that there is, at some level, you are forced to look into a full expansion. But again, I'm not sure.
In the Tiering model, if I remember right, there are 2 ordered entities around. One is associated with the scale, Gaussian, whatever, beta function. And it's broken in principle. You don't know whether the beta function vanishes or not. And the other has to do with this chiral gauge inverse that you mentioned, the axial one. But there's a Jacobi identity. You apply one, then the other, and then the other. And that gives an iterative proof that the beta function vanishes.
Okay. I think so. You're going. You're jumping ahead for those.
No, I'm saying that there's a principle behind it.
I agree. I mean, the point is that in order to use the comparison in this context, you have to compare with Tiering-like model or Tiering model with the right cutoffs. Typically, Tiering, the solution of the Tiering model is a bit delicate. If you you change cutoff, you may change some aspects of some details of the solution. So in particular, if you use a momentum cutoff, there are some. Okay, so you enter a delicate grounds, and we have to compare with the right momentum regularization of the Tiering model or lattice model to be able to conclude something on our lattice theory.
I also, I still didn't completely comprehend the point why you need to look into these W's. So suppose I told you that the beta function vanishes. Suppose you knew that already. Would you still have to do that, or do you have to do that to deduce that the beta function vanishes from the Tiering model? So suppose you already know that the beta function vanishes, right?
Okay, maybe. I don't know. I don't know. In our procedure, somehow it goes together. Okay, another thing is that my impression is that if you want detailed properties such as analyticity of certain coefficients, which we use here and there, you need, or at least it's convenient to expand everything. So this is something maybe I don't know sufficiently well the inductive argument. Typically in the inductive argument, you lose powers of lambda, if lambda is the strength of it. You lose powers of lambda to control certain estimates. You don't really get analyticity, for instance, optimal scaling in lambda of all the kernels, and even less analyticity of the kernels. So again, I'm not sure. So in our proof we rely on knowing properties of this sort. So it's hard for me to answer to say that this is specific. So maybe, yeah, I don't know.
Well, one thing you've said, Alessandro, is that you only know that the beta function vanishes by comparison, and the comparison only takes hold in later orders of the renormalization group. So initially it might not vanish.
No, initially it doesn't. In fact, what we have to show is that our beta function is a dominant part plus a rest which is a priori summable. The rest is easy to see that is summable, but it's not zero.
That's the point I'm making.
Yeah. The dominant part is the same as in the Tiering model, and that is vanishing. Also in this decomposition, to show that this the decomposition, I don't know, we use this structure also in the proof of this decomposition. Again, I'm not sure this is needed, but since we use in a lot of places, it's hard for me to isolate one specific point.
I think we can probably, the thing to do is to see your proof, and then somebody can write down a 5-line proof.
I would be, because this is the typical thing. Why don't you do that? Don't do it.
No,
I'm very happy to.
My question was more naive, I think, because I don't see this beta function around. So
No, in fact, because I'm not getting
about that formula.
You will not see even on Friday.
No, but I see this formula, no, and then I can ask myself, can I do the bounds?
Yes. At this level, at this level.
Can I do L1 bound? I mean, can I just have a norm on the potential and iterate?
Yes, this here you can. Yes.
Okay. You need an L infinity bound too, I guess.
Huh?
You need an L infinity bound as well in order to iterate. You use the
No, I think it's enough the L1 because when you take the L1, you have to integrate over all these points. And, no, I think it's enough the L1, or maybe a weighted L1. But yes, you can do it.
Well,
and in fact, in the inductive proof, this is exactly what you do. You assume inductively something about this bound. So at a finite number of steps, you for instance, 1. You can say.
What got on this thing is that the infinity one which is needed over there. Yes.
Okay.
But for the G, not for the W.
That's for G. That's not.
But these these summed over SVJ was exactly the bound on the L1 bound on W minus 1. So if you want to first make the sum over SVJ, you reproduce the bound on W on the L1 norm of W1, and that is inserted here. Maybe this would have been clearer. see what you mean. Maybe I should have done that way. Too late. I think I. Okay, so, and if you now go on after after a number of steps, we have this situation here. Where V of H as kernels WH, which admit the same kind of bound, written now in this expanded form. So sum over these 3 tau. So now these 3, we can do the following. We can also associate these scale labels to the, so we can say that the root here has scale -2, this vertex B0 has scale -1, this corresponds to the expectation of scale -1 associated with this node B0, this at scale 0. Here I have trees with root on scale h and endpoints. I have sum over set of external these lines coming out of the effective vertices V, with the constraint that PV0 should be equal to L of what? Of product over V not endpoint. So all this this point where you have branching, all these branching points of what? Of C to the SV G HV omega 1 to the SV -1 G HV omega infinity minus SV -1. There should be a minus SV -1 here. Okay, it's at the exponent. And here I'm using the convention again that for each V, I have this each V as its own scale label HV, and it's the number of branching the number of lines that are exiting to the right, which I call SV. This is just an iteration of this.
The lambda to the end.
And then we have lambda to the alpha. Okay, so that's it. And now we should recall what's the behavior of these guys. So GH of omega, if you remember, I wrote it out just for -1, but this behaves like 2 to the h G0 of 2 to the h times 2 to the h1. So that's a specific scaling. So this means that the L infinity norm of GH is essentially 2 to the h, while the L1 norm, recalling that we are in 2 dimensions, this is this 2 to the h times the contribution from the integral, which is 2 to the minus 2h.
What have you written there? V not E.
Not endpoints, so all the branching points.
Okay.
So these 3 continues up to scale. So the last branching points are on scale 0, and then you have endpoints that correspond to the Vieri interactions. Okay, so in this formula I can replace. Oops. So I get alpha to the n taus on a family of trees with n endpoints and root scale label of the root h, product over v, the branching points, not the endpoints, c to the sv, and now I have what? I have 2 to the hv. Yes, I have this 2 to the minus hv, sv minus 1. The L1 norm is like 2 to the minus h. And then I have 2 to the hv. And I have this sum over I, pvi minus pv over 2 minus sv minus 1. Okay, that's it. So I want to understand. I want to rewrite this in a more useful way. So first of all, I want to understand how this norm scales with h. So in order to understand how it scales with h, let me do the following. So each of these guys I write like this. So I will have some overall scaling in h plus certain rescaling factors depending on the scale difference.
So Alexandra, the fact why you have this factor of 2 for the L1 norm? It's not.
Oh, I wrote infinity twice. Okay, this is just 2 to the h times an exponential with rate 2 to the h in 2 dimensions. So you have to take d2x of e to the minus. Sorry, there is an additional 2 to the minus 2.
Yeah, it's not correct.
Yeah, so that makes
Yeah, it
sense.
was a 1 here.
The L1 norm is getting worse.
Is it okay?
Yeah.
So it's like the same times the dimensional factor associated with the integration d to h, which is 2 to the minus 2h.
So that's actually going to be L infinity. The more L infinity norms you see, the happier you are. And the more L1 norms you see, the unhappier you are.
Yes. Yes. Okay, so I want to understand the overall scaling of this guy. So I have 2 to the h, and now I have sum over v to the right, the not endpoints to the right of the initial guy of what? I have minus sv minus 1 from here. There was a minus in front. And then I have plus sum over I p from 1 to SV I minus PV over 2. And then I have another minus SV minus 1. So I have minus twice this guy. Okay, so there was a minus SV minus 1 here, and minus SV minus 1 here. Okay, now, first exercise. If you played a little bit with trees, these are not surprising. If you never, you have to think a second. So if you sum over branches minus 1 over all the branching points, you get the total number of endpoints minus 1. And if you sum over V this thing, you see that there is a telescopic structure. So you are summing the PVs of the following points minus PV of the following vertices minus the one of the vertex you're at. So if you sum over all vertices, you have a telescopic sum. You're left just with the sum for the endpoints minus this guy for the first point on the left. So overall, you get 2 to the h minus 2n minus 1 plus the sum of these PVIs for the endpoints for n minus this guy PV0, which was L, divided by 3. So remarkably, the dependence upon n simplifies exactly, minus 2n plus 2n, and you're left with 2 minus L. And the fact that the dependence upon n simplifies is a signature that the theory is renormalizable, but just renormalizable, not super renormalizable. This is referred to as the scaling dimension. Of the kernel with L external length. If you like the effective vertex with L external length.
Where did the minus 2 in front of the SV minus 1 come from? I lost that.
Yeah, there was a, let me
Top
write,
right.
there was a 2 to the minus h, which I wrote as minus hv, which I wrote like this, SV minus 1. There was a minus in front. This was the 2 to the minus h coming from the L1 norm to the number of guys on the spanning tree. And here there is 2 to the h times all the guys outside the spanning tree. This is all the guys minus those in the spanning tree. So if you like, this is a 2 to the minus 2, 2 to the minus 2h coming from the integration. You can say that each propagator has a 2 to the h. That's why before I distinguished the 2 to the h from the 2 to the minus 2h. You have a 2 to the h for each propagator and then an additional 2 to the minus 2h for each line of the spanning tree. So this 2 to the minus 2h, so this 2 is the dimension, if you like. Okay, so we can, this h we can erase and put in front of everything 2 to the h 2 minus m over 2. This is a scaling factor. If you like, this can be rescaled together with the external lines attached. So you remember, this is a contribution to the effective potential that has psi smaller equal than h. This psi smaller equal than h has natural scaling scaling properties, and this can be reabsorbed in a rescaling of the field, if you like. But now you're left with these other scale jumps here. And now the scale jumps, you can manipulate them in a very similar way. So you have hv minus h. You write it as, so if you have, let's say, v is here, h is there, so I decompose it in a sum of contiguous scale jumps along the path that on the tree goes from the root to v. Okay. This W, so this W is something in between, and W prime is the parent vertex in the tree. This is W, this is its parent. Okay, so W prime is a number of children. Okay, if I do so, HV SV minus 1 can be rewritten as sum over W larger equal than V0 sum over V larger equal than W as V minus 1. And so what do you get? Well, this is the same as before. You get the total number of endpoints following W on the tree. Okay, and you do the same here, and you get exactly the same formula, the same telescopic sum, but only for the subtree originating from V.
Sorry, are you insert this sum over V bigger than W?
Yes, so here,
yes, sorry.
yeah, so I'm zooming this.
Yeah. Yeah.
Okay.
Yeah. Yeah,
and then I have to do the same here. So, and I do exactly the same. So again, I will write HW minus RW prime, blah, 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 and I get the same kind of telescopic sum, but relative only to the subtree originating from V instead of the total tree.
No, and I don't get the formula you wrote. When you separated the last line.
Yeah, this is the same as this, but relative to the subtree. Yeah.
So,
relative to the subtree, maybe no, sorry, it's the other direction. No, it's okay. It's okay.
Yeah, just V is a different variable.
Yes, so with the subtree with root W.
Yeah, because you have a V on the left.
Yeah, this should be depend on V.
V is a fixed thing or not in this formula? I don't understand.
Maybe V0 is not.
Yeah, you're right. What did they do? You're right. Yeah. Thank you. Yeah, I'm just summing over V this expression.
Yeah.
Okay. By the way, the C to the SV is again just a constant to the power n, again because of that factor. So what do I get here? So let me get this. I will write a very similar formula. So if I do this, so this product over V becomes 2 to the minus sum over V larger equal than 0, this. Then I have exactly the same kind of formula here. 2 to the sum over V larger equal than V0 of HV minus H, this other thing. I use, so here I use this formula. I use the analogous one for the other factor. And I get that these two guys become product over W not endpoint 2 to the hw minus hw prime of exactly the same kind of formula as before. Again, the dependence upon n vanishes, and you're left with now renaming this WV 2 to the HB prime 2. Okay, this is not surprising, and again, maybe I could have given a more transparent one-step proof. So I realized that maybe I could have. Anyway, so you say you have this external scaling dimension here. Internally, you have similar factors, but now associated with scale differences. Somehow you have to iterate, you have to rescale properly, and the scaling dimensions. This is what naturally you get. So I just the result. So notice that these scale differences are always positive. HV is a vertex, V prime is its parent, so this is positive. No, it's whatever.
So you,
Well, no, it's larger or equal than 1.
there were a constant like CSV at some point.
Yes, there is some other constants to the n, because again, say to the SV, you add and subtract 1. So the plus 1 becomes C to the number of branching points, which is over there n, and here again you use that and becomes C to the n. So there is some constants to the n that includes the effects of all those constants to the SV. Oops. Okay, so let me just conclude with basic. So the key thing for next time. So you see now that in terms of the scaling dimension, you can now really recognize what are the potentially dangerous terms and the terms that are fine. So you see that whenever this guy here is strictly negative, all these exponential terms are exponentially decreasing. So you lose memory somehow of all the v's that have more than so 2 minus pv over 2 is negative if and only if pv is larger or equal than 6. This is 0 if pv is equal to 4, and this is 1 if pv is equal to 2. So when you sum over, oh, here there was a choice over with the constraint that pv 0 is equal to 1. When you sum, so all the terms that have PVs that are all larger or equal than 6, note that here these are just, you're not including the endpoints. So the endpoints always have 4 external lines, but all the other terms you can decide have 6 or more lines. I mean, this is a class of contribution to this sum. So those terms have these terms that are all exponentially decaying. And it's easy to see that if you restrict the sum to PVs that are all larger or equal than 6, you're fine. You can perform this sum, and you get constant to the, well, the minimal n you can have, alpha to the minimal n you can have, times the scaling factor. But there are really terms where you have some effective vertices with 4 or to two lines, and those terms have a problem. I mean, this you cannot sum over the scale differences. Of course, as long as you iterate these to trees of finite level, you will be able to do it. But if you want to iterate up to h of order log L, you won't get anything sensible unless you do something with the terms with 2 and 4 lines. So, okay, I was hoping to start saying something about what you do with those, but I